Hello again. This is part 2 of our statistics webcast and PowerPoint review, and I hope you will be able to follow along with me on this aspect. I want to be sure to talk about correlations because correlations are used very often in education and social sciences. Correlation simply shows the relationship between any two variables whatsoever. For example, is there a relationship between height and weight? Yes, there is a relationship, and you would expect it to be a certain described in a certain way. I'll talk more about that in the next screen. Correlations do not show cause and effect. That is, you cannot take a correlation and say that one thing causes the other, one factor causes another, but you can predict certain things. For example, you cannot say that just because a person is taller, they are going to weigh more. The fact that they're taller does not cause them to weigh more. The fact that they eat 7,000 calories a day may be the cause, after all. But they do enable prediction with some degree of certainty. I can predict with some degree of certainty, not absolute certainty, but some degree of certainty, that if a person is taller, I can predict that they probably are going to weigh more than someone who is shorter. Of course, that is not perfectly true. Correlations are indicated by a correlation coefficient, some decimal between negative 1.0 and positive 1.0. The general principle is that the farther away from zero in either direction, the stronger the relationship. For example, a plus 0.25 correlation would not be as strong as a negative 0.26 correlation, because the negative 0.26 correlation would be further from zero than the positive 0.25 correlation. So we're looking here at absolute value, if you will, for those who are math people, or you're looking at the difference or the distance away from zero if we're talking about a number line. All right? So correlations are indicated by a correlation coefficient. The most common correlation statistic is called the Pearson R. Pearson R, like the little letter R. In statistics, that always indicates a correlation, and Pearson is the primary test of correlation. You see here three graphs on the screen, three maps, if you will, of factors. If you look on the left-hand side of the screen, you have examples of a positive correlation. If you look at that particular grid as a graph, then you know that as one variable goes up, the other variable also goes up. That is a positive correlation. So there are many examples of that. Just like I said, the taller a person is, the more they weigh. It's not always true, but it is generally true to some degree. Of some number between 0 and positive 1.0 would represent that correlation. I'll give you another example. There is a positive 0.62 or 65 correlation between ACT test scores and college GPA. In other words, the ACT score of a student can predict what their college GPA is going to be with a 0.62, 0.65 degree of certainty, if you will. There is that kind of relationship. Now, does a higher ACT score cause a higher GPA? Heavens no. It doesn't cause it. You can only say that there's a relationship that enables you to predict that the higher the ACT test score, the higher the college GPA is going to be. The second graph in the middle of the screen, the negative correlation, is the opposite of that. As one variable increases, the other variable decreases. Okay? As one variable increases, the other variable decreases. And this might be illustrated by the relationship between weight and exercise. The more you exercise, the less you would weigh. Is that a perfect correlation? Wish it was, but it's not. But it does allow prediction that if a person exercises more, we can predict that they're going to lose weight. All right. Another negative correlation, the number of cigarettes a person smokes and the number of years that they live. The more cigarettes they smoke, the fewer years they're going to live. That is a negative correlation, a negative relationship between those two variables. And then on the right-hand side, you see an illustration where there's no real connection between the two variables. There's no pattern to the points there. Is there any relationship between, gee whiz, any two factors, the amount of coffee a person drinks and the color of their hair? Well, no, I don't think there's any relationship there. So there would be no, even if the amount of coffee went up, the color of the hair would not change. So there's no correlation between those particular two variables. Examples of correlation. I just told you about height and weight. As one variable goes up, the other goes down, up in a positive correlation. It's not perfect, so it's not going to be 1.0. I guess an example of a perfect correlation would be the number of people who are dead and still breathing. Okay? There is a perfect correlation there. No one who is dead is still breathing. All right. A negative correlation coefficient is caused by one variable going up and the other one going down, as we stated earlier. Here's some questions in the educational context. Is there a relationship between the amount of instructional time and student achievement? Well, we would say yes, we think so. As one goes up, the other goes up, right? That would be a positive correlation. So we can do a particular statistical analysis of how much instructional time students receive and their achievement. And is there a predictive value there? And of course we know there is. Another example, how about the number of days absent in student achievement? Well, we know that the more days a student is absent, the more their achievement scores are going to decline. So that is a negative correlation. As one goes up, the other goes down, generally, a negative correlation. We can't say necessarily that being absent causes achievement to go down. We just know that we can predict if a student is out more away from school, then their achievement and learning is going to be impacted by that, decreased. But there's no direct cause and effect. The only way you can determine cause and effect is in a genuine laboratory setting that controls all of the other extraneous or confounding variables. In this particular example here at the top of the page, is there a relationship between the amount of instructional time and student achievement? There are a lot of other variables that can impact student achievement besides instructional time. The personality of the teacher, for example, might be one, or the temperature of the classroom, or any other number of things, access to technology. Any other number of factors might impinge on any result that would negate you being able to conclude there is a cause and effect relationship, a direct relationship. So we have to be very, very careful about that. A regression analysis uses correlations to understand how dependent variables are related to the independent variable. In other words, you're trying to decide is there a relationship and what the strength of the relationship is between any number of variables and a particular dependent variable. And if you read the last paragraph, what happens in a regression analysis is that the experimenter or the researcher or the statistician, if you will, holds all of those confounding variables constant while assessing the correlation between one of the variables and the dependent variable, the one which changes are measured. For example, all of the things that I just mentioned a moment ago, the teacher, the instructional time, access to technology, and so forth. If you have measures for all of those things, you can perform a regression analysis and see how strong the relationship is, how much each of those factors contributes to the overall student achievement increase or decrease. I hope that makes sense. The bottom line here is, in short, this method of analysis holds all but one of the independent variables constant and measures the effect of that one, then repeats for each one. The result is an indication of the effect size of each of the independent variables. So you might get different Pearson R's, that is, different correlation coefficients for each of those things. You might see that the teacher is related to achievement at a 0.45 correlation, and the access to technology might be 0.35, and then the classroom environment might be a 0.15. In other words, you see the strength of the correlation and the effect of each of those variables on the final outcome using a regression analysis. All right, this page gives you another example of that, and I'm not going to take time to look at that. You can certainly read it for yourself. Chi-square is another interesting and quite simple little statistical metric that is used. It's also called the goodness of fit test. It measures how closely an observation actually matches or fits a prediction. For example, if you're going to flip a coin and you're going to flip it 10 times, you might expect that you would get 5 heads and 5 tails, right? That would be certainly expectable. When the actual flipping is done and a specific count is observed, you get maybe 7 heads and 3 tails. Then the chi-square statistic can be used to evaluate how close your actual data is to what you predicted. How well does your outcome fit what your prediction was. This is pretty valuable when you have a prediction. For example, an intervention is supposed to create X amount of increase in test scores in math. Well, that's the prediction. Then when you get your observation data after you do the intervention, you can compare your original prediction, or what the company says it's going to produce, with what actually happened and see how well those two things actually match. Chi-square, simple but very valuable. A factor analysis, I give you this just simply because some of you are going to use this later on if you do your own investigation and things. Factor analysis can be used to simplify data, such as reducing the number of variables in regression models. For example, a pilot test or questionnaire survey of 25 questions using a Likert scale, that's like a 1, 2, 3, 4, 5, from little to much, could be evaluated using a factor analysis to see if there were redundant questions or groups of questions that were really measuring the same underlying factor, thus making it easier to group or to reduce the number of questions or to completely eliminate certain questions as contributing nothing to the factors themselves or the constructs. I did a particular study, and a pilot study a number of years ago, and actually did that. Had a number of questions. I started out with about 40 questions, and it ended up being 24 questions because some of them were asking for the same kind of thing. Others of the questions did not contribute anything to the overall analysis. The regression number at that point was very, very low, that is the correlation, and so we kicked those out. So that's a real review of statistics, and you have a little quiz that you're going to have on Blackboard, and there's also a chapter in the textbook that corresponds to this statistical summary.